Alright, so this is Math331, Lecture 16. This is a really good day for class presentations on problems because I have spent too much of yesterday lifting snow and shoveling snow. This truck doesn't seem too heavy, but it reminds me too much of white fluffy things right now, and I would be very happy to be putting this down at least for a little bit. So the plan for today is I want to finish up the division problem that we talked about first, then have you guys present some of the problems you found interesting, and then if there's time, start the integration unit. I know I have not given you stuff to read for the integration unit. This is deliberate because the name of the techniques tell you how to attack the problems. Some of these techniques on integration I think you've seen before, others I don't think you've seen before. And it's nice to get a familiarity with a new way of looking at problems. I was talking with somebody yesterday from the class about which is more common, the pigeonhole principle or monovariance, and a lot of it is what you're used to. So how many of you have ever watched like Looney Tune cartoons? So do they use the best classical music, or do we think this is the best classical music because this is what we've been exposed to growing up? This is of course a question beyond the realm of a math class. We will leave that for our colleagues in the humanities to answer. Alright, so let's recap the problem. It does hurt holding the chalk. So we want to divide n as a1 plus an. N is 3. In case 1, all the ai are positive integers. In case 2, the ai greater than 0 are real. And the goal is to maximize the product a1, a2, an. Okay. Let's do case 1 first. The integer case. Any thoughts on how we should attack this problem? Yes.
We want all the a's to be close to as close to each other as possible.
Okay, why do you want them to be close to each other as possible?
Because if you can think of the case where a1 and a2 are say 2 apart, you can each put them. You could, like if a1 was 2 and a2 was 4,
okay,
or n and n plus 2, increasing a1 and decreasing a2, you can show.
Okay, so what you're claiming is that if you have two numbers x and x plus 2, you can compare that to x plus 1 squared.
Yeah, and there's always going to be an improvement.
And this would be x squared plus 2x, and this will be x squared plus 2x plus 1.
Yeah.
So this tells you that you can never have numbers that are 2 or more apart.
Yeah.
Related to this is we've done the Farmer-Brown problem in this class. You have a fixed amount of perimeter. So if you have, and then when you have the Farmer-Brown problem with a fixed amount of perimeter, the best you can do is a square. So if we have, x, y, with a semi-perimeter which is fixed as x plus y, and we want to maximize the area which is xy, we've seen that the best we can do is when x equals y. So if two numbers were not equal, we could replace them with the average.
As long as that's an integer.
As long as that's an integer. So at least for the second part, that would be useful. For the first part, not so much. But so we know this observation, the observation you just gave us a moment ago, if it's an integer case, that we do not want things to be too spread apart. If we use our result from real analysis, at least in the case when everything is real, we actually have a maximum existing by real analysis. And then you can say, since the maximum must exist, if two things weren't equal, that'd be a problem. Right. Let's go back to the integer case. Can you rule out any numbers? What number should be very easy to rule out?
All ones.
All ones, or any ones. Because if you have any one, it's not going to help the product. So clearly, 2 is less than or equal to each ai. What about large numbers? Could we rule out a number like 10? Could one of the AIs be 10? Initially, it seems like it could be. But then what might you notice?
10 can be written as 2 5s.
10 can be written as 2 5s. And so we could then increase the product because 25 is bigger than 10. Rather than doing 10 as 2 5s, I would actually like to do 10 versus 8 plus 2. 8 plus 2 is 16. I can write 9 as 7 plus 2. I can write 8 as 6 plus 2, all the way down to 5 as 3 plus 2. And this shows me I'm never going to have a 5 or higher. And that's the nice thing about always writing this plus 2. If I write 10 as 5 plus 5, if I write 8 as 4 plus 4, it's going to work, but I'm having a different decomposition for each one. Could I have any 4s?
It's the same as 2 2s.
It's the same as 2 2s. It's getting exactly back to what you just said with things being at least 2 apart. But if I have a 4, I can break it up into 2 2s and I'm indifferent. So I can say, there shall be no 4s. And so now we know all the a's are between 2 and 3. Okay, that's a lot of progress. So the question is, which would we rather have, lots of 2s or lots of 3s? And we're trying to maximize the product.
Lots of 3s.
Okay, why 3s over 2s?
If you can split it up into a bunch of 6s,
good.
you can compare 3 squared versus 2 squared.
So we can compare 3 2s and 2 3s have the same sum. The product here is 8, and the product here is 9. So what we would rather do is, whenever we have 3 2s, it's always better to replace with 2 3s. So it comes down to, you have a bunch of 3s, and then 1 or 2 2s at the end as needed. So the final solution is as many 3s as possible, then 1 or 2 2s to finish. What if we have just the number 1 left over? What if I give you a number like 100? That'd be 33 3s. And I've got a 1 left over. What do?
You do 32 2s and 2.
Right, not 32
Or
2s.
3s and 2 3s.
Right, then what I do is I take that 1 and I combine it with one of the 3s and make that into 2 2s. So if you have a 1 left over, you combine the 1 with the 3. If a 1 left over, combine with a 3. Okay, so this completely solves the integer problem. So the interesting question is whether or not the real problem will be easier or harder than the integer problem. One of the advantages is we have results from real analysis that an optimum exists, but there is a configuration that will work. The difficulty is now we have much more freedom. Okay, now one question of course is whether or not it's worthwhile to have a bunch of really small numbers and then get some really big numbers. Can we say any of the real numbers can't get too large? Well, the sum can be higher than n, right? So the largest any of these numbers can be is n. If I let one of the numbers be 0, it's just going to decrease the product. So I could work on a compact set. I could work on a closed bounded set. So for the real case, there's no issue in terms of being in a situation where I can apply these results. Okay. Doesn't want to pivot. I'll try moving it back just a little bit today. Okay. So now the question becomes, how should we look at the real case? What can you tell me about the restrictions on the AIs?
Aren't they all going to be equal?
We don't know that yet. What's the easiest first condition we can get on the AIs? Yeah, greater than 1. If you want to keep things compact, we would say greater than or equal to 1. But if anything is less than 1, just add it to something else, and you'll increase the product. So we know 1 is less than or equal to AI. How large could it be? Do we have an upper bound?
I mean, our initial upper bound would be n.
Our initial upper bound would be n. Can we do a little bit better than
n?
n?
Easily show that it's going to be a bit better than that.
Right.
So like square root of n would probably be.
Well, can we take anything from the integer case? What was the upper bound from the integer case?
3.
So we may not be able to do.
Would it be 4?
Yes, it would be 4. So the same argument as before works to show that the AES can't be larger than 4. And we know things have to be somewhere between 1 and 4. We don't really need this. We can solve the problem without it. But it's nice to get some rough idea of where things live. And so this would be the compact space things live on. Yes?
What about the case where we consider the upper bound to be big N divided by little n? That is the average of all the AIs.
Well, if you take that as the upper bound,
We don't know the value.
then you would have to say everyone would have to be exactly the average. Because if one of them was greater than the average, another one would have to be.
Yeah.
Right?
Yeah.
So, but the other thing is little n is free. We don't know what little n is.
Okay, yeah.
So what we want to, so one good way to attack this problem is to do for each little n, find the best. So let Fn be best for a given n. And so now if I fix little n, what's the best I can do?
Big N divided by X.
Yeah, so we would get little Fn, each piece has to be the same as all are equal. So we've actually solved this a few times, I think, in this class. The other thing is, since we have a compact space, since we have a closed bounded space, we can use this result from real analysis. There is a maximum. If 2 of the pieces weren't equal, we place them with their average value, and the product goes up. It's just the Farmer Bob problem. So we know that in the case when we are given what little n is, the best we can do is all pieces are the same. And now we want to optimize this function. Why could this function be a pain to optimize? It's integer valued. Well, it's not integer valued, I'm sorry. Its inputs are integers. So instead, let's look at the closely related function. F of x is n over x dx, which you could write it as e to the x log of n over x. And let's optimize this function. Now, almost surely the real max of this is not going to be the integer max. But maybe we can pass from the real to the integer. We can do that if the function looks something like this. If the function goes up and then goes down, the real max will be here, and then the integer max will either be the integer immediately on the left or immediately on the right. So if we're fortunate enough to have a situation like this, we can pass from the real to the integer max. This is typically not going to be the case. Given that this is a problem that I'm choosing to present and spend a lot of time on, odds are that this will be one of those lucky problems. This will also give us a chance to talk about curve sketching again, which seems to be a technique that was not really covered in your calculus classes. I can understand why this is not being covered in the 21st century. Oh, this is an interesting question. None of you took calculus in the 20th century, correct? Right? You were just barely alive in the 20th century. Right? Things have changed since I was a young graduate student teaching. Okay? So, curve sketching is typically dropped. It's really not a bad idea to understand curve sketching. So let's look at the first derivative. The first derivative tells us a lot of information. Since this is an exponential function, it's just the function itself times the derivative of what's up top. So we get to use the quotient rule again.
Product rule?
Oh, sorry, product rule, sorry. Product rule. So we're going to have the derivative of x, which is 1, times the log of n over x. And then plus x, and now we want the derivative of the log of n over x. Well, the log of n over x, this is the same as the log of n minus the log of x. So when I take the derivative of this, It's just 1 over x with a minus sign. I have an x, so this becomes the log of n minus x minus 1. What number has a log of 1? It's just e. So this is just f of x times the log of n divided by xe. So if I want to find the critical point, we need f prime of x to be 0, so that means n x over e equals 1, because the log of 1 is 0, so that means x is equal to n over e. So now we can use this to do our curve sketching. Let's see if it works. All right. So now let's look at what's going on. So here's my x-axis. Here's f prime. If I wanted to make a beautiful sketch, I would calculate f double prime and find where it's concave up and concave down. We do not need a beautiful sketch today. Okay? So here's 0. Infinity somewhere down there. And the other point we need to worry about is the point n over e. So the first derivative is 0 at n over e. Let's look at the derivative for x less than n over e. When x is less than n over e, n over e divided by x, this is going to be a number that is greater than 1. What can you tell me about the log of a number greater than 1? It's positive. So I know my function, if the first derivative is positive, my function is increasing. And when x is greater than n over e, I have the log of a number less than 1. So it's going to be negative. So I know it's something like this. This is not a great drawing. It does not need to be a great drawing. It just is enough to give a sense of what's happening. Now the other thing is, instead of studying this function f of x, I could have studied the function log f of x. And we talked on the pre-pi versus e day about why you might want to look at the log of a function. It sometimes simplifies things. Does it matter for this one if I look at the function or the log of the function? Would it have helped me to take the log? Should I have listened to my own advice? I've got a product here. If I don't even listen to me, why should you listen to me? Yeah, I see a lot of you nodding your head. Yeah, why are we listening to Professor Miller? Does taking the log help me here? Not really. I've got an exponential of blah. If I take the log, I'll just have blah. But when I take the derivative, the function is just floating outside here. Since it's an exponential, it's never 0, it's always positive. And I just have the derivative of blah. It's the same calculation. I just have f of x floating along for the ride. It's not going to affect the shape of things. It's not going to affect where the derivative is positive or negative. So for this problem, there's really no gain in taking a logarithm. And this is the level of curve sketching. Now all I need to do is check the integers immediately before and immediately after. So we can pass from real max to integer max. And we want little n to be approximately n over e. And if you want to be really specific, it would be either the floor of n over e or the ceiling of n over e. It's one of those two values. Two values is not that bad to check. And what's going on is we're saying we want to divide into n over e pieces, approximately. How big is each piece? Each ai is approximately how big? E. Alright, so let's draw one last little picture here. Here's 2, here's 3, here's 2.5. Where's E?
2.71.
Okay. E is closer to 3 than it is to 2. Does this have any connection to anything else still on the board?
3s were preferable to 2s.
Yeah, 3 seems to be preferable to 2. I'm trying to still find where to put this today so that it will pivot. I've had enough exercise shoveling snow. I don't need to be walking to the camera today. There we go. Okay. So 3 is closer to E than 2 is. And over here, we're using more 3s than we are 2s. Is this a coincidence? Or is this really related to, is the fact that we want more 3s really related to trying to maximize these products? So I'm going to post a nice article in the additional comments for those of you, especially those of you who like computer science. What base should we program in if we're working with computers? There's a couple of bases I will accept. Give me some candidates. Base 2 is natural. On, off, yes, no, true, false. Dark side, light side. Original Trek, new Trek. Lots of things can be split into binary.
But if we do base 3, we can keep
Base
many
3,
more cases in the same number.
Base 3 turns out to be more efficient for disk storage than Base 2. In terms of how fast algorithms run, Base 2 is often better than Base 3. But in terms of some storage issues, Base 3 actually has proponents. It's not an unreasonable base. So Base 2 is good, Base 3 is good. Sometimes in computer science we'll also use Base 8 or Base 16. We also like to use Base 10 because we have 10 fingers. And there was one other base I think we've seen this semester. Much, much larger number than 10. With heavy stone tablets. Did we do that in this class? The Babylonians? We didn't do Babylonians in this class? Oh, okay. I will then just quickly mention this, and then we'll move on to student stuff. Okay. Any questions about this problem first, before we move on? So this reviews a lot of our stuff from calculus. It reviews curve sketching. It reviews what the derivative tells us. The derivative tells us where the function is increasing and decreasing. The curve sketching gives us a good shape of the curve. And it gives us results on passing from real maxima to integer maxima. So a lot of good stuff in this problem. After these student presentations, we will then start doing some integrals. And how do you evaluate integrals? For the most part, Calc 2 is the greatest lie of any math class we would take. We spend a lot of time as well, actually, I don't. I've never taught Calc 2. And I'm going to try to go my entire professional career never teaching Calc 2. Now that I've gone several decades, I think I can do this. Once I filled in for somebody at Smith College to teach one day of Calc 2, but they were really doing Calc 3 material. So I thought it was okay to fill that in. But I'm trying to see if I can do it without. Because I hate lying to my students. Calc 2 is all about lying. We do all these integrals, and we make you think you can integrate, and you can't. We have to do a lot of work to get these cookbook problems where you have a nice closed form solution for the antiderivative. Most functions don't have a nice closed form solution. All right. So we haven't done Babylonians. All right. How many seconds in a minute? 60 seconds. How many minutes in an hour? 60. Why are we working base 60? Why would the Babylonians like base 60? How many degrees in a circle? 360. Somewhat coincidentally, there's almost 360 days in a year. Now that one is beyond the Babylonian control. I don't think they got to choose where the Earth was in terms of, something like that. But a lot of these other things they got to control. Why would the Babylonians like 60 so much?
It's divisible by a lot of times.
It's divisible. Let's start listing divisors of 60. 1, 2, 3, 4, 5, 6, 7. Wow, finally found a number that doesn't work. 8 doesn't work. 9, no. 10, yes. 11, no. 12, yes. 13, no. 14, no. 15, yes. So huge number of divisors. Lots of nice ways of splitting 60. And you can even look at what fraction of your numbers are divisors. And it's extremely high. If I chose a prime number, the only divisors would be itself and 1. So 60 has a good number of divisors. It splits things up nicely. So what I want to talk about is efficiency. So I'm assuming none of you got the joys of shoveling snow yesterday. I don't know exactly how bad it ended up being I think we easily hit 20 inches. I know one place early in the day was saying Williamstown had 19 inches. Here's our driveway. And I started the day by I would take 2 shovels at a time, one in each hand, and I would push the snow like this deep into the lawn. And so for a good chunk of the day, I am shoveling constantly this section of the lawn and just pushing the snow this way. Why would I be shoveling the lawn like this?
You like your lawn?
No. I mean, I was really looking forward to playing baseball with my kids and having the lawn again. Why would I spend time shoveling the lawn? This could be useful, you may not use a lot of the math I teach you, but maybe if you have a house years from now and you're unfortunate enough to live in a place that gets lots of snow, this could be useful.
I mean, like, if you put it right next to the lawn, the snow can just fall back onto your driveway.
One is it could fall back, but the other thing is it's going to get higher and higher and higher. And it's going to be harder to shovel the snow above, and you're going to have to really pick it up and really toss it high. So if you keep doing it like this, I start here and then slowly over the day, this moves inward. The other thing is, one of the expressions you will learn is the plow giveth and the plow taketh. And so a little bit after 8 o'clock last night, my son and I were out shoveling. We finished the driveway yet again, and then the plow came and put a giant wall of snow at the base of the driveway. This is the first time my son said, look what it did to Mount Cameron. Yes, Mount Cameron is now over here. And so by having the strategic reserve over here, is when all the snow came here, we then run in the street like World War II battle plans. And instead of having to shovel this above things, we could actually just shovel it into the pot over there. Shoveled it again late last night, woke up this morning, the plow had come back and put more snow at the base of the driveway, and did this again. The strategic reserve is now gone. But it did its job, because at the end of the day, you're tired. You want to do as little heavy lifting as possible. So you really want to think, what can you do to make things efficient? This is a different type of problem solving. What kind of problem solving do Babylonians have? It is related to heavy lifting. Okay? I am not deliberately doing this to tie it into the snow. I'm not planning the entire semester like this. I'm not that good. However, given the fact that I have spent so much of yesterday shoveling snow and lifting, I think this is an appropriate time to talk about the Babylonians. What heavy lifting would Babylonians have to do? So you need to know a little bit of history, but this is a liberal arts college. Right? You're supposed to know stuff like this. Let me check my notes. Really easy to pick up notes. Nice. What did the Babylonians have?
Tablets?
Tablets, right? They would have to lug tablets around. Okay, everybody know the multiplication table, 9 times 7?
60.
Wow, that was too pitiful. That was bad. 4 times 8?
32.
All right. 12 times 11?
132.
All right. 9 times 12? Did you actually know that, or did you quickly compute it?
I don't know. I can't tell.
I quickly computed. I know up through my 11s. My 12s I kind of know, and I can kind of quickly compute. Does anybody know their 13s or 14s? Why not?
Why would you?
Why would you? Exactly. Right? We use a place number system. We use a positional number system. If we can do multiplications from 0 through 9 with 0 through 9, we can then build up bigger things. All we need is a multiplication table. And then we use a positional. Lord help us if we wanted to do this in Roman numerals. So for us, it's basically, a 10 by 10 table. What would the Babylonians be? $60 by 60, 3,600. Okay. So one possibility is you memorize the 3,600 multiplications, versus memorizing the 100 multiplications. I can't prove that this is why there are no longer any Babylonians around. Now, is it really as bad as 3600 and 100?
No.
Okay, what can you do that will help?
Well, it's symmetrical, so you can divide by 2, and so you can just count the number of pairs.
Right. Now we've got to be careful because you also have the time when they're the same. So if we divide by 2, it would be 50. But have we double counted a little bit, or have we undercounted?
Both.
Chip!
Well, we've double counted some things, but because 10
So-
by 10 is not.
I think we've counted, if we're dividing by 2, what we would really want to do is we would first want to add all the doubles. So we would really want to have 110. And then we would divide by 2 and we get 55. This is because xy equals yx, and then add back the x squareds. So here, we would really have, I think, 3660. And then divide that by 2.
Much better.
And so then it would be 1830. Proportionally, it's the same game in the two cases. But it's a far more meaningful game for the Babylonians. Now that's still a lot of tablets to either lug around or memorize. If you're a young Babylonian scholar, going into the family business, you do not want to have to memorize 1,830, nor do you want to have enough tablets with you to have 1,830 things. So the Babylonians had a great way to multiply and reduce it even further. So x times y is x plus y squared minus x minus y squared over 4. And you could also do x plus y squared minus x squared minus y squared over 2. And if I just expand this out, this is 4xy divided by 4, it's xy. This is just 2xy over 2, it's just xy. So rather than multiplying two numbers, I'm going to, in this case, do 2 multiplications, 2 subtractions, an addition and a division. In this case, I will do 3 multiplications, 2 subtractions, an addition and a division. Okay, well this one clearly looks a little bit better than this one. But I'm doing more multiplications. And I've got a division by 4. And I've got more additions and subtractions. Why is this a good idea?
Now we only need to know 60 square number.
Yeah, now we only need to know the squares. So the idea is if you have a table of squares, you can use the table of squares. So this is the idea of a lookup table. And it's either 60 or maybe 120 because we're going a little bit higher. That's much better than 1830. And in fact, if you were to let things get higher and higher and higher, let's say you had the Super Babylonians who were looking, base 600. Then this would be, 600 squared divided by 2. So this is going to be basically on the order of base squared over 2. This is going to be on the order of twice base. It's going to be a square root of the other one. It's going to be an enormous savings. The idea of a lookup table is one of the most important ideas in modern mathematics and engineering. Rather than having to do a lot of calculations, what you do is you do a couple of key calculations and you save them. And then you use those to derive other quantities. You could teach an entire semester on the idea of lookup tables and how you interpolate between values. So here, we do simple operations to get things exactly. I'm going to risk asking this even though you're probably all too young. Have you ever used a lookup table to calculate like the value of a logarithm or the value of a trig function or the value of a normal distribution at a various point, and it's not a value in the lookup table, and so you have to somehow find a way to interpolate? When I was in high school, we actually had to learn how to use lookup tables. It's another lost skill. But Here, it's a perfect interpolation. We can pass from these values to whatever we want. But in general, if I have two values, if my function is continuous, maybe I take the average value of the two. Or if I say I'm 30% along the way, maybe I will take 30% of that difference and add it here. Or maybe I'll somehow try to estimate the derivative and get a better idea. And so there's lots of things you can do to get good estimates. Okay, so this was the idea of the Babylonians and just doing things efficiently. Given that we started by talking about the multiplication problem today, it's not a bad one. It goes well with doing things efficiently. Is there anybody willing to present a problem that they found interesting and be recorded for the class? Excellent. So what I'm going to do is you're going to become the instructor. I will have you introduce yourself because we have some people who'll be watching this remotely. And I will give you the device. So speak clearly. And so you want to put this down, somewhere like on your shirt over here. It should just clip on. You want to have it closer to your mouth, like over here on your shirt or coming in over there. Exactly. On the waist over here. So I will move off to the side. Okay.
Hi. I'm Wei. I'm a computer science and math major. So I will talk about a similar puzzle to the milk puzzle, and I will talk about how to use computer science to solve. So our problem is we have a lake and two bottles A and B, and bottle A can only contain 3 gallons, and bottle B can only have 5 gallons. And we want to take water from the lake into the two bottles, such that bottle B has 4 gallons. So when I say we can just take 1 gallon by 1 gallon, but we don't have a measuring device, so we have to somehow use those two to jug the water around and get 4 gallons. So let's try to do this step by step. So initially we start with empty. But this problem is a simple variant of the milk puzzle because we have only 2 cups, and 4 is special because 5 minus 3 times 2 is 4. So we can use the difference between the 2 to get a 4. So that's how we do this problem intuitively. So let's try to get a difference by first filling bottle B. Then so A can take 3, so we can just pour everything from here to here. So you have 3 here, then 2 here left. Then we empty this here. 0, 2, then 2, 0, then 2, 5. So then we have 4 here, so we're done. So that was easy because we had only 2 cups. So
So one question, is that the fastest way to get 4?
We can also do 2 times 3 minus 5 plus 3. So first we fill bottle A and then pour the 3 gallons into B, and then we fill bottle A again and pour the 3 gallons into B. We'll have 1 gallon left in bottle A, and then we pour everything out. We empty bottle B, and then we pour that 1 gallon into B, and then we get.
Yep, that also. So the question is, is that chain fewer or more steps than this? But given the fact that we now have a bounded number of steps, we can quickly switch the space and see if there's anything faster. But just an interesting question to see what's the fastest way to get there, not just how to get there.
So if we have more cups and more options to the cups, so one problem arises is whether we have a solution at all, or do we have the shortest solution. So maybe you can interpret this question in another way. So let's set the point A, B, denote the gallons of water in A, and B is the gallons of water in B. So basically our solution space is just going to be a graph where here is 0, 0, and here is 4. 1, 2, 3, 4. Because we're starting with, so this is A. Because we're starting with 0, and we can go up to 3 gallons here. So then we're going to have 6 here. So if we draw our solution from here, it's basically starting from this point, 0, 0, going over to 0, 5. So we draw an arrow here. From here, 3, 2. And so on until we get to the point 3, 4. So if we were doing this by hand, we have to draw like every possible edge that exists, then find a path from 0 to whatever point is on this line. So we should also consider doing this by computer because it's faster and easier. So what we can do is for each of the points in the solution space, we will have basically we'll have a adjacency list. So it's like a lookup table, except you have the vertices here. So like when this is 0, 0, then you have all the points that's adjacent to this point in the column. So like 0, 4 can be here.
Wait, 0, 4 or 0, 5?
0, 5, yeah.
Okay.
Yeah, so 0, 5 can be here, or you can do 5, 0. 5, 0, or you can do...
Oh wait, so I thought the second component was... A is the first component, B is the second component. So it is 0, 5. It is 0, 5. It's 3, 0, and 0, 5 are the two adjacents.
But this is the B axis.
Oh, you put B on the x-axis and A on the y-axis. Okay.
Yeah.
Okay.
Yeah, but you get the idea. So
Yeah.
it's basically
Okay. Yes.
all the vertices here, all the adjacent vertices here. So now we can use some algorithms to search for paths from the initial point to whatever point that's on here.
Right.
So usually we have two algorithms. One is called DFS and one is called DFS. So the idea with DFS is if we have a graph that looks something like this. We're going to start at the starting point. Then we're going to choose one path to go down until we can't go down anymore and we backtrack. So for example, we're going to go here, then here, then here, then there's nowhere to go, so we're going to go back. Then we find there's another one here. So we're going to go here. Then we back all the way here, then we search this stretch again. So that's why this is called depth first. But one problem is with this algorithm is that if one particular path is super long, the algorithm will be stuck on this particular path. And the solution might be like right here. So that's DFS. And for BFS, suppose we have this again. Instead of going depth, we'll go breadth. So we're gonna start from the starting point. Then we keep tracking in memory all the frontiers. So that's like everything that's a distance d from the starting point. So we're gonna go to here, and then next we explore those. So the good thing is we never get stuck in any solutions. But the problem is we're using too much memory for this. Because we have to vertices. So that's the two algorithms we have. So for this particular problem, we might use BFS, this one first, if the number of vertices in the solution space is small. Because we know that from each vertex we have finitely many other vertices we can go to. But if we have more cups, then the branching factor, so branching factor is how many other vertices we can go to at one particular vertex. So if this gets big, then we're using too much memory. So after some point, we can switch to DFS. So by using those two algorithms, we can solve the problem using.
Excellent. You get it done. So I'll take this back. Right, okay. So this is actually an extremely common, powerful technique. Is you might have two different algorithms, and you run with one of them for a while, and if it's working well, great, and if it's not, then you pause and you go to another. And so a lot of times they do this in sorting algorithms that one thing works very well, but there's a small class of data sets that it fails on. So run with it for a while. And if it's working, great, and if it's not, consider and switch to another one. There's a whole class of problems that can be solved like this. The idea is to have a mechanical way of going through the space. Think of it like the quadratic formula versus looking at divine inspiration and just seeing the roots. If you can just see the roots, that's faster. But sometimes it's harder. So I'll end with a problem for you to think about, and I'll probably make this a homework problem in the future. You have a bridge, but it's dark, and you need the flashlight to get over. And you have 4 people, and you're poorly drawn, and their names are 1, 2, 5, and 10. Their parents were extremely unoriginal. They named them based on how fast they thought they would be able to walk in the future. So it takes 1 minute to walk across the bridge, 2 minutes, 5 minutes, and in a great shocker, 10 takes 10 minutes. You can only walk across the bridge if you have the flashlight. So the question is, what's the minimum number of minutes it takes to get everybody over? And you want to show that you can do it in 17 minutes.
So can only one person go on the bridge?
I'm sorry, 2 can go at once. At most 2 at once. Because otherwise, of course, you would just have everybody go with 10.
So when, for example, when person 2 and person 10 are walking together,
they go at the speed of the slowest. Right. You have to walk at the speed of the slowest. And then we're running out of time, but does anybody know a movie where this jug problem is shown? Plays a key role in a very interesting, funny movie. This is your chance for cultural extra credit. You've got 3 seconds left. It is not Princess Bride. That's a good movie. Samuel L. Jackson is in it. Die Hard 3.